So, good morning, everyone. It's lovely that you spend part of your Friday morning with us at Neo4j. My name is Jim Webber. I'm Neo4j's chief scientist, which means on the good days I get to develop software. And today I'd like to talk to you about some of that software that the folks at Neo4j build in the field of graph native technology. So technology that's natively built to handle graph workloads. So to that end, we've got a short agenda here. I'm going to give you an overview of what graph native technology is. We're going to have a friendly little bit of computer science, so I have to earn my job title as chief scientist by doing that kind of thing. We're going to have a look at some database architecture at a very high level, and we'll look at how different design and implementation choices make databases good or less good for certain workloads. And then we'll contrast that with the way Neo4j works. We'll look at why Neo4j is built from the ground up to be native for graphs, and why that matters for end users. What are the trade-offs or advantages and disadvantages we get when we use a graph native technology over a non-native piece of tech. Towards the end, then I'll quantify some of the themes that we've looked at throughout the rest of the webinar. In particular, I'm going to cover off some performance advantages of our graph native tech versus non-native graph tech, and then we'll do some Q&A at the end. So hopefully that all seems pretty interesting for your Friday morning webinar. So let's get stuck right in. First up, some assumptions. I live in a world of graphs, and it's become clear to me over the last decade or so, since I've been working with graphs and then ultimately came to build graph technology, that graphs are the most important data structure on the planet. If you don't believe me, think about the fact that Google with its graph displaced Yahoo. Think about the fact that LinkedIn with its graph displaced Monster. All of the Facebook with its graph displaced everything, including democracy, hilariously or sadly. So graphs are super important. They have energized a whole raft of new technical platforms and innovation. And quite happily, most workloads, most domains actually can be conveniently modeled as graphs. And I have a slight lament there that in my previous life, all of this clever modeling I used to do in SQL databases in tables, and the liberation that I felt when I first picked up graph tech and found that I didn't have to deal with extraneous complexity anymore. So these assumptions underpin all of the things I'm going to discuss this morning. I think they're true. You may accuse me of confirmation bias, and that may also be true, but I hope to convince you also that graphs are the most important data structure you'll ever deal with. So what about some science then? How do I earn my stripes as Neo4j's chief scientist? Well, this is strangely and unhelpfully becoming more and more the way I actually look. But I want to talk about some computer science, actually. Nothing too crazy. I'm not going to ask you guys to invert a binary tree on a whiteboard or anything evil like that. I want to think about this data structure. Now, many of us will have done computer science at university, and one of the most fundamental data structures we'll have learned back in the day, or perhaps snoozed through those lectures, but we learned about things like lists. And here we have a very vanilla data structure, something very simple, an unordered, singly linked list. Nothing controversial. Hopefully that fires a few neurons for you from your university days. And this list, it's kind of interesting, right? We often, it's easy to kind of glance over a linked list as being terribly uninteresting, but it's actually got some quite interesting properties. In terms of if we want to add to this list, because it's unordered, I can add anywhere into this list while maintaining its invariance, because unordered is a particularly easy invariant. So if I want to add something, it's great. I just stick it straight in. In the more formal computer science terminology, we'd say that's O1 or constant time. And that's great because that's super cheap. It means no matter how big your list is, if it's a list of 3 items, as it is here, or if it's a list of 3 trillion items, adding to the list is theoretically the same cost. So for writes, this humble, unordered, singly linked list is actually pretty cool. The flip, though, of this list, this unordered linked list, is that if you want to read a value from the list, if I want to know whether I as a customer exist in this list. It's much less good. I have to, because it's unordered, I have to typically read most of the list, right? It's what's called an order n in computer science terminology, meaning not that I have to take all n steps for n elements, but that as the number of elements in the list grows, the amount of effort it takes to find an item in that list grows linearly. Now, linearly for relatively small structures is sometimes acceptable, but for large structures, linear is pretty poor. Admittedly, it's not as bad as some of polynomial or something, but if I had a list of 3 trillion, doing 3 trillion I/O operations down to disk would be perhaps prohibitive. But that doesn't mean the lists are a write-off. Not at all, right? We know that these lists are amenable to fast uncontended write performance. So what I could do is I could put a box around it, put an API on it, and voila, it's a database. I mean, it's kind of a trivial database, but it's a database, and it's a database that's quite good for uncontended writes. That would be its native model. I could now market this as a NoSQL database that's really good for uncontended writes. I'm sure that there's probably a niche out there for that. Of course, generally speaking, most databases want more than one client. They want to be able to have contended or concurrent activity. So the list really isn't so great then, because we'd end up having to do some locking or something, and we'd cause contention around our insertion point. But actually, there are techniques that we could use even to make this a useful database, even for concurrent activity. So we could use things like CRDTs, so conflict-free replicated data types. And the CRDT is not magic. It's just a data structure that has a merge rule associated with it. And of course, merging an unordered list is easy peasy because there's no ordering, so you can't really violate any problems, any constraints there. So CRDT would allow us, each of our clients to write to their own little local list, and then there'd be some merge down the line where our master list would come along. You could do other things that would be clever here. You could perhaps take the approach that the disruptor folks did and say, well, you would allow contention to happen, but you'd make the contention windows super small. So you would have, for example, all of your concurrency control code running in userland, where it runs quickly. There's no cache destructive behavior going on. And in such cases, even if you're doing sequential inserts, you can still get many millions of those per second. So this list is not to be ignored. It's quite profound in a way, but it is native. Its native model is for writes, contended, or if you make it a bit fancier, uncontended writes. It's not good for reads. It's not good for searching. It's not good for holding a graph structure. This isn't the structure, the Uber structure that we'd use in Neo4j, for example, to store graphs. But if I had a situation where I natively needed high sequential write inserts, then this would be fine. So it's a native model. We can generalize this though, right? So we know that lists aren't the be all and end all. And the next thing we often learned in computer science 101 or in data structures and algorithms 101 was a tree. In this case, I've sketched up a simple binary tree. There are much more interesting trees that we could discuss. Now, the lovely thing about a tree is that for reads, to find an element in a tree, and in this case, a binary tree illustrates this perfectly. To find an element in the tree, it's log n, which means every time you take a hop, half of your problem space evaporates. You can stop considering it, which means that if I have a million-sized tree, it's going to take me a maximum of 6 hops to discover whether my item is in the tree or to locate that item. And 6 is way better than a million, which is what we have to do in the humble singly linked list case. The flip, though, is that a tree is also log n for writes, because first you have to find the right place in the tree to deliver your insert. So compared to the list that was O1 for writes, the tree kind of forces us to make a compromise, which is way better for reads, but degraded with respect to the list with respect to writes. However, if I've got a tree, I also have the ability to spread write load. So it's usually the case that in a tree, when I'm writing values in, I can write them concurrently because I don't always target the same part of the tree to attach my new node. So I effectively have a front along the tree. It's leaves to which I can attach new data, and that means that I get contention spread around the structure. So that's really nice. Of course, we don't have that in the linked list case where we have to do clever mergy things or clever mechanical things to make that work. Now, as a database person, I love trees. Databases, if you remember your databases lectures at university, it was full of trees, usually B trees or B plus trees for on-disk databases, with the idea being that the non-leaf nodes of the tree would be in memory and they provide a really fast, kind of RAM order of magnitude speed index over the actual records themselves, which would then be on secondary storage. That's a very classic model for databases. More recently, we've seen people use things like B plus trees, which is the classic B tree, plus a kind of linked list of the leaf nodes, such that you can also do scans without having to do index operations. But we also know that tree structures need to rebalance. We need to manage them. And occasionally, tree rebalancing can be an expensive and blocking operation. So again, we have a trade-off where trees seem to be working brilliantly for us, but then we hit some pathological insert pattern, and then we have to potentially perform a rebalance. The important thing here is there's no such thing as a free lunch. You have to go in with your eyes open and realize if you're going to build on top of a tree, it gives you some beneficial characteristics with respect to reads and reasonably priced rights, but then occasionally you may have to reorg your data structure. So what? So what does this matter for us as people building IT systems? Isn't this just Jim, ranting or reminiscing about his university days? Well, not quite. I do think that we have somewhat a duty of care to look a little bit below the surface of any product we're using. And we have to choose the products that have appropriate data structures and algorithms that suit our workload. In some cases, the implementation of a system, of a database, will empower you. It will enable you to do your work, your application work, the stuff that makes money or provides value better, faster, cheaper. And in other cases, it will inhibit you because you'll be going against the grain of that system. So for example, a B-tree-based database might be a good idea for SQL stores or document databases versus like a hash ring style database, a hash map database might be a sensible basis for producing a distributed column store. But neither of these, it turns out, are sympathetic to the kind of locality and access patterns we're seeing in graphs. So in Neo4j, we have to pick the right tool for the job. If you hammer away at this screw for long enough, you can declare that you've got a multi-model screwdriver. But really, we want to pick the right kind of implementation to do the job properly. Now, let's get this out there. I can't claim nativity as any particular aspect or solely of Neo4j, or indeed of the graph technology family. All databases have a native model, and in fact we've seen these throughout the period of NoSQL provenance. We've seen things like column stores, key value stores, and document stores. And these models have products which have implementations that are optimized for those models. So you see things like Cassandra, it's built on this wonderful hash ring style idea so that data can be spread around a cluster evenly. We've seen things like MongoDB, document databases, which are built on the kind of classic B tree, where you have an index that sits atop the documents that ultimately store your application data and so on. So each of these databases has a native model. And I'm going to speculate, having not seen the implementations of many of these databases, but I'm going to speculate they're really good at that. I realize that, at some level, all the databases are competitors with one another, but I really genuinely believe that the people who build Cassandra, the people who build MongoDB, and so on, they're pretty smart people, and they really know how to optimize for the job that those databases do. In the same way that my engineering team knows how to optimize for the job that Neo4j does. The thing that where it starts to get a bit more unsure is when you then stretch that primary model, the native model, to do something that's non-native. I think one of the biggest problems you have there is that you have a bunch of infrastructures already in place that goes with the grain for a particular model, for documents, for columns, what have you. And then you say, well, actually, if I just put some API or some tweaks around the edges, suddenly I can cover off some other model like graph or relational or whatever. And the point is, knowing the way that certainly my database is built, the underlying engine simply isn't optimized for that. It's optimized for its native workload. And so any add-on, any other model don't benefit, generally speaking, from the evolution and the love and the dedication that's gone into the primary model. And indeed, if you're a user of the secondary model, you get short shrift, right? All the love goes into the primary model because that's where the community is, that's where the customers are, that's where we've invested hundreds of engineer years. But some folks have spotted the enormous graph trend. Graphs are growing and have been growing for several years now, faster than any other database type, and they're jumping on the graph bandwagon. Now, from a commercial point of view, I salute you. That is probably a reasonable thing to do. But from a technical point of view, we have to assure ourselves that what's under the covers of this thin veneer of graph can actually do the kind of graph operations we need it to do for valuable production systems. I see two approaches out there in the wild. I see graph layer, where we take an existing data store and we bolt on a graph API from an open source library or something, and then declare victory. We do graph. On the other side, we take an existing data store and we extend its query language with a graph keyword or something like that, and then declare victory. Architecturally, they kind of look like this. So in the graph layer model, you have a graph API where you have things that talk about vertices and edges and that kind of stuff. Then you have a translation layer, which translates between your API and the foreign data model, like a column store or relational database or whatever. On the graph operator side, you've got an existing query language that you have extended with some graph operator, and that graph operator binds down onto some conventional usage of that document store. Now, this doesn't look so bad at 30,000 feet, except you can kind of already start to worry a little bit about some of these things. So, the graph layer, in the middle layer of the graph layer case, that has to do a lot of work, right? It has to do a lot of translation work between two quite distinct models. It has to worry about things like data safety, transactionality, it has to worry about locality and performance. And the underlying database actually doesn't provide any help there. It doesn't know that it's being used as a graph, so it merrily continues to do its existing model things. Similar story on the graph operator side. I've got something like a popular one here is a document store. I've got a graph operator, but unless that document store is being used in an exactly conventional way that suits the graph operator can't process graphs on that store. So a well-meaning user can effectively ruin your graph just by using that document store as a document store. Worse than that, of course, in our world, in the graph world, we see that there isn't any cipher in these layers. Cipher is the de facto standard graph query language. It started out life on Neo4j, now through the auspices of OpenCipher. It appears on Apache Spark, it appears on SAP HANA, it appears on, I think, several other reputable databases out there. But typically, if you're going this way, there's no cipher. So you're out in a minority community. The graph layer it implies excessive denormalization in order to try to get performance. And that denormalization implies complexity and it inhibits performance. On the right-hand side, the graph operator and the structure of the document store, the fields in the documents that you have to store, requires convention at the user level. The document store simply cannot enforce any of these graph conventions because it doesn't know about graphs, which means that, again, a well-meaning user can come along and ruin your graph. And ultimately, these engines, they may well be amazing engines for what they do, but they don't understand graphs. They can't prevent dangling relationships, which is logical corruption, which ruins your graph. All you can do is hope, and hope is not strategy. So the graph layer, take an existing data store, bolt on a graph-like API from a third party, and declare victory. If we think about how this might be implemented, we think that a popular style might be something like a column store, a hash map-based column store. Now, lovely picture of Japanese knotweed, by the way. They're a non-native in the British Isles, of course. Now, the Graph API suffers because most of the data, database engineering, is focused on the existing model. Graphs aren't a hobby or a tick box. I can tell you for free that I have a very large engineering team who focus on nothing but graphs, and then they're not trivial to make safe and performant. They certainly aren't something we would ever consider bolting on the edges. Now, the upper layers in this kind of model, particularly the translation layer, will try to optimize this. They'll try to square that circle. But what we found in looking at these kind of hacks is that they can kind of, the denormalization works to kind of order of magnitude 1 hop, 2 hops, maybe 3 hops. But once you get past that, the denormalization, you can't denormalize to infinity. The denormalization fails you, and generally at 3 or above levels deep, the traversals become incredibly slow. Now, at first you're like, well, that seems fine, Jim, because I just want friends and friends of friends. And I would agree. In that particular social use case, that's fine. You can find friends of friends transitively, and it's probably going to work. But actually, most use cases with graphs aren't 2 or 3 levels deep. They're many levels deep. Because even friend of friend, I actually want to find products that friends of friends in my neighborhood have bought. Already now I'm at 4 deep. I want to find out what's going on in my data center. I want to find out what's going on between applications that sit on top of containers, that sit on top of operating systems, that sit on top of blades, that sit connected to backbones, that sit connected to switches, and blah, 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 blah. I'm already 27 levels deep at this point if I want to find single points of failure, or if I want to do some root cause analysis and so on. If I want to think about my medical records, I'm 42 years old, which is a very auspicious age for a nerd. But because of that, it means I have a really long medical history. And it's not served well at all by 3 hops deep. How many hops on your train ride to work in the morning? How many hops on your Mars mission? Certainly more than 3. Now, the limiting factor here is that a popular graph approach would be to use a hash map under the covers. Now, hash maps, in theory, are lovely because they give us order 1, constant time lookup for reads and writes. The downside is that hashes aren't mechanically sympathetic to graphs. A good hash function tries to spread data around to keep it balanced. And of course, when you generalize that to being a distributed hash map, one of these hash ring style databases being distributed around even means across machines. A graph, on the other hand, adores locality. If I'm a node and I'm connected to some other nodes through relationships, I really want those nodes that I'm connected to be close to me, physically close to me in memory, so that I can traverse across those relationships to them very quickly. I don't want them to be in a different page. I certainly don't want them to be on a different machine if at all avoidable, because those things are expensive. I've now broken the mechanical sympathy of my computer, wherein I could simply do pointer lookups, pointer resolution, and I now have to do clever things. And those clever things going across the network, finding out loading pages from disk and so on is expensive. So you'll go from, on my laptop here, I can do about 16 million traversals a second on a laptop, right? And as soon as I start to do clever things like get page misses because of locality problems or go across the network, then that collapses down to maybe millions, maybe hundreds of thousands of traversals a second. It's far slower. Worse when you add in those limitations around denormalization up to depth 3, and then you add in latency for the distributed hash ring, and you find that these kind of systems, because they're not native for graphs, they've never thought about graph locality from the ground up, they end up being quite slow. Here's a lovely plant as well, Himalayan balsam, beautiful plant, non-native again in the United Kingdom. And the idea here in the graph operator world is that we would have some kind of keyword in the query language that looks up graphs, and we'd use some conventions, some user-level conventions in the existing model to infer linkage that the new operator can bind to. The downside of this is there's no native support for those links. They are simply fields in a document, keys and values in a piece of JSON, which have to be processed, computed, resolved, looked up in an index before you can do the hop. Compared to Neo4j, by the way, where resolving your path across a relationship is an O1 lookup. It's a multiplication, actually, of ID by pointer size. This means that traversing links are slow. The data structures aren't designed for graphs, nor are the store formats. The actual data on disk is not at all designed with graphs in mind. It also means that you need clever workarounds in order to use these as effectively as graph databases, and you reach the limits of those workarounds very quickly. You simply can't do much in the way of deep traversal with these things. How many hops again to traverse your data center? How many hops on your train ride to work? How many hops on your Mars mission? More than something that's doing inefficient index lookups can do. Worst of all, I think, if you disobey these conventions, because the database won't enforce linkage, it won't enforce referential integrity. It's a document database in this case. Documents are allowed to evolve independently. That's their key USP. If you disobey those conventions, then the graph operator in your query language simply ignores your graph. There's nothing in the machinery to enforce it. Now, these kind of databases are popularly implemented as B-trees, and as I mentioned, databases love B-trees. As a side note, no one really knows what a B-tree means, whether it means balanced. Does it mean Boeing, where it was actually invented back in the day, or does it even mean Bayer, who invented it? We don't know. But we do know a lot about how B-trees work. We know that B-trees work at log n, but the underlying model doesn't know about links. So you've got this kind of awkward thing where I've got a document structure, the database knows about that and can work with it and index it and all that good stuff. But then inside my user data, I've got this super important structural data, which some operator up the stack is meant to know about. So the fact that the underlying model, the underlying data structure, the underlying DBMS doesn't know about graphs means that it's not very good for general purpose graphs. You can't denormalize in any arbitrary pattern in order to suit my graph workload, my social network versus your medical system versus their Mars mission system, and so on. If you delete documents out of this B tree, you're probably going to leave dangling links, because the document engine doesn't, by design, for performance reasons, for good reasons in its primary native model, have any referential constraints. More generally, this means that you as the user have to enforce those constraints, which is now placing a bunch of database work onto you as the app developer. And you're probably a great app developer, but you should feel a little bit sore at databases that force you to do the work of databases. I think that's pretty unfortunate. And so it's also easy to unintentionally ruin your graph. Another user, another app has a view of your document database that is truly a document. They don't know that they're meant to be enforcing these graph conventions that you rely on. And then, of course, you mix in the network for latency and failures and data loss and so on, and you get into trouble. I'm going to suggest that we should pick the right tool for the job. I'm very much a fan of the Unix philosophy, a tool that does a job well. This notion of I am a database that can do columns and graphs and time series and SQL and it's not terribly believable. You may well have APIs that expose that functionality, but your internal implementation is always optimized for your primary model. Neo4j's implementation is always optimized for the graph model. And we see this, right? These kind of, these aren't superficial things. These are fundamental database design considerations. We choose our data structures very carefully to support graph workloads natively. If you choose to use Neo4j as a B-tree style document database, it's not going to be as good as a database that's designed for that up front. If you choose to use Neo4j for graphs, though, it looks great. So over time, we've seen, many people measure themselves against Neo, and some, as they say, there are lies, damn lies, statistics, and vendor benchmarks. But our qualitative experience is that at trivial levels of connectivity, 0 to 2 hops, a very low degree of connectivity, small numbers of connections, just at that asymptotic part of the chart, you can probably, Neo4j and MySQL are approximately similar. But as you start to get past thousands of connections, as you want to do many hops through the graphs, as your connectivity is increased, as your degree increases, then we start to see many orders of magnitude advantages in using native graph tech and using Neo4j. And you'll often see things that will take minutes on a non-graph database, will take milliseconds when you've got them in Neo4j. And you don't take my word for it. There are people out there doing this. We have a Fortune 50 retailer who had record Cyber Monday sales, about 35 million daily transactions non-peak. Cyber Monday went through the roof. Each transaction, each recommendation is somewhere between 3 and 22 traversals, hops. And each of these recommendation queries are executed in 4 milliseconds or less, replacing some legacy software based on relational. Marriott, the famous hotel chain, performed 300 million pricing operations per day. Pricing, of course, is a very, very sophisticated dependency graph, and they can get about 10 times the transaction volume on about half the hardware compared to relational. A really nice presentation from Graph Connect on that from 2016. This pricing is 7 to 22 hops per transaction to try and figure out the price for the room that you're buying at this point in time. Again, but if you look both the Fortune 50 retailer and the Marriott example, typically their average hops per transaction is far larger than a non-native graph database would come to be able to deal with. The real-time packaging and routing, we have Neo4j runs routing for the largest postal service in Europe. They route 7 million odd packages a day with peaks of about 5,000 routing operations per second. And routing is sophisticated, right? This postal service is one of the larger countries in Europe, let's say, and routing around that country is complex. Trying to figure out, how to do efficient routing is naturally a graph operation. Our engine, our query language, our APIs make that straightforward for these guys to perform a vital service for that country. A couple of ones that I'm particularly interested in. Qualia, I heard from a colleague of mine, is an ad tech company. They have about 90% of the US population in their database. And of course, ad tech is a very low latency business. You need to get your ads out within the bid time, otherwise your ads don't get shown. They're really interesting stats here. So they have about 90% of the US population where they try and figure out that you are you on your iPhone and on your desktop and on your iPad or whatever. About 1 billion transactions a day, 3 terabyte graph, 5 billion nodes. Kind of an impressive thing, and all of this to do super low latency graph operations to figure out an identity on the fly so that graphs can be, ads can be sold. If you ever log into eBay and use their amazing Shopbot AI, the underlying model for that is Neo4j. So the underlying database that stores all of that clever AI model is Neo4j. One final thing, Asi Barak, who's at K-Hut in Israel, ran up Neo4j. He was relatively new to Neo4j at the time, spins up Neo4j on an AWS i3 instance and poured data in. 10 billion edges and growing, lovely performance results, ingestion rate of 4 billion edges or 4 billion relationships per day. This native graph stuff is pretty fast. So here's our graph stack. Here's our native graph stack. This is a high-level architectural view of Neo4j. So where's the magic? Well, I mean, look, you can read the source, right? If you're so inclined, if you want to find out how we do it, we're open source. You can read it. But really, let me give you the magic in English prose rather than Java code. At the lowest possible level, we have on disk a format which is optimized for graph traversal. Effectively, we enable on disk and in memory, we enable you to do pointer chasing to traverse the graph. In fact, we separate out graph from data, and we put the graph part of the structure in fixed size records which have O1 access, and we put the user data, those properties and so on that you store in Neo4j, in other structures that typically have log access. This is one of the reasons you'll often hear Neo4j folks saying find the nodes or data you're interested in first, and then retrieve the data. So you get wonderful query performance. On the right channel, Neo4j is transactional. We're ACID transactional. And we have right bucketing, so we can trade off a little bit of latency for amazing throughput, even though that we're ACID transactional. Even on my laptop here, which is a laptop, I'll get about 4,000 ACID transactions a second through Neo4j in a out-of-the-box database. On your amazing production hardware, you're going to go far better than that. On the read channel, we have an optimized off-heap cache, and this ensures that most traversals run in RAM or in fact, or better. Our compact pointer representation in the high-limit version of Neo4j means that we can fit more pointers in memory, and more importantly, more pointers in L2 cache, where it really, really, really goes like a rocket. At the top of the stack, we have Cypher. Cypher is by far the world's best graph query language. It's based on a bunch of other query languages, historical query languages, SQL, Sparkle, Gremlin. All of that learning, all of that pain has been synthesized into Cypher, making it, I think, right now, hands down, the best query language on the planet for graphs. You can see that it's being taken up now outside of Neo4j through OpenCypher. It's amazing. Our implementation of Cypher is underpinned by an extremely high performance runtime, which is sympathetic to the underlying graph store. So we have a bunch of statistics being generated as queries are run, and our query planner for Cypher takes into account those statistics when it's making an optimal query plan for you. For example, we can try to create queries that, whilst returning the correct results, will try and find cheap routes through the graph, places where connectivity is low, and therefore we need to perform as few IO operations as possible. And all this is possible because we own the whole stack. We're native for graph workloads up and down the whole stack. In Neo4j 3.2, we added a bunch more native thinking into the stack. So the Cypher runtime is now compiled rather than interpreted. We added composite indexes and native label indexes, moving away from the general purpose indexing toolkit that's Lucene provided most of our indexing historically, to more graph-affine indexing that we want to go forward with in the future. Cost-based optimizer in Cypher is now the default. We have query depth optimizations for distinct. We have effectively affinity between keywords that we depend on up in Cypher land, up in user land. We can now optimize for that actually in our graph engine. We still, in our world though, we have this lovely query language, we've got this lovely optimizer and query planner, we've got this mechanically sympathetic approach where we aim to work in main memory or better, and we've got this great IO performance where we do graph traversal by pointer chasing. But we also provide ACID semantics to keep your graph safe. Now, ACID nowadays doesn't have to be inexpensive. ACID is having a renaissance. And if you're interested, there are some really good papers on coordination avoiding transactions by Bayliss et al. Out of Stanford. But meaning that transactions aren't all that expensive compared to weak models like eventual consistency. But transactions from a user point of view, they're gold dust, right? I mean, knowing that data is committed or not is just phenomenal. And so Neo4j, we try to make this work for you. Now think about the ACID transactions in the context of a production system. So if you try to create a production-ready cluster of Neo4j, we give you certain guarantees about consistency, quite strong guarantees actually. But if you've got a cluster of non-native tech that you're trying to pretend is a graph database, the underlying consistency models prove problematic. Most notably because most databases you're going to put non-native layers on are eventually consistent, and that's a problem. Now, in distributed systems, there's an inherent trade-off which FLP, the Fisher, Lynch, and Patterson paper highlighted way back in 1985. So this is something that predates the famous cat theorem stuff. And ultimately, what it boils down to is this. A system can be available, that is, it can accept a read or a write even when faults occur, or it can be reliable, and that is, a system can produce the correct result even when faults occur. So let's put this into more engineering terms. Availability means I can give you the wrong answer when machines fail, and reliability means I will not give you an answer when sufficient numbers of machines fail. And that's a really interesting trade-off, and they are irreconcilable. We know that. So what do we do? Well, aggregate databases like column stores or document stores or so on have to just agree on one value. If I place a value into a column family, I know that that value will be replicated eventually to all of the replicas in the system. Now the strategy varies. You can do clever things like vector clocks or interval tree clocks and reason about causality and total ordering and so on. Or as we do in Neo4j, you can even have a consensus protocol if you could afford such a right path. You can even do daft things. You can even have like things that are unconscionable, like last writer wins by wall clock time, and then this winning value gets synchronized across the replicas, hopefully. Unfortunately, graphs need consistency of two. They need two different replica sets to agree, and that's actually a fundamentally more difficult problem. If I'm writing a relationship between two nodes that happen to be in different replicas, both sets of replicas need to agree on the existence of that. Otherwise, you've got non-determinism, and that non-determinism is corruption. So having two records need to agree means that we need reliability to agree upon those two values. Availability, therefore, the thing that most NoSQL databases are optimized for, is a bit of a liability. Let's take a look how that would play out in, say, a document store. Here I've got a document store. I've got a record representing the United Kingdom. I've got a record representing the United States. And as you can see, node ID 1, the United Kingdom, has an outgoing loves relationship to node 0. And node ID 0 is the USA, and it agrees that there is an incoming loves relationship from node 1. This is good, this is stable. If you were to traverse this graph, you know that Britain loves America, and America is loved by Britain. This is a wonderful setup, all political statements aside. But what if we had some concurrent activity? What if the French came along and removed our love for America while we're busy on the other side of the system increasing our love for America, value 100? If you ask the question now, does Britain love America? The answer is, I don't know. And databases shouldn't be able to say that, right? Databases should know the data that's in them. In this case, I've got two incompatible values. If I traverse from America to Britain, that seems great, still in love. But if I traverse from Britain to America, no love. I can't traverse that route anymore. So I've got this horrible non-deterministic behavior, which will effectively lead me to create logical corruption in my graph. Based on the direction I traverse, I may choose to fire the missiles or not. And that's rather a worrying thing. So for graphs, actually reliability is far more important than availability. They need consistency of two support. We must favor correctness over availability. Otherwise, you'll get logical corruptions that will spread through the graph and cause your graph to be unhelpful, to be useless, actually. This is a surprise. Oops. Oh, that's heartbreaking, that one. It was surprising to us when we did the R&D work a few years ago, back in 2010, 2011, to discover this. But we've rebounded from that rather unfortunate surprise, and we've now taken a very strong opinion about how consistency should be for graph databases. And in fact, Neo4j offers causal consistency here in Kyle's model. Kyle, of course, writes the Jepson distributed systems testing tool. Now, in Neo4j, in some senses, we're quite a conventional database. We have a transaction log. You'll be used to the notion of logs if you're familiar with things like Apache Kafka. And all servers in Neo4j have a log, and the idea is that we want to keep the logs in sync. And it's by adding commands to those logs that ultimately mean that graphs get populated. But as you can see here, these logs are at different states. That's okay. Those logs will be consistent shortly. It's just that because of the speed of light, the messages haven't, log entry 11 hasn't been transmitted to the bottommost logs just yet. Don't worry, this is normal behavior. In any distributed system, even the ones that are strict two-phase locking, blah, 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 scary stuff, you still have the speed of light. That means you can't have your God's eye view consistency at all times. But although this is normal behavior, surfacing this to the user is a pain. Imagine this. I've got an app, and the app says you need to log in to continue your purchase. Okay, so here's my opportunity to log in, but I'm going to create an account. So I create an account, and then I log in, and then, oh, no account found. Oh, well, I'll try that again. Log in. Oh, login successful. Oh, look, those systems are there. We still encounter those systems in our daily lives, and it's weird and frustrating and horrible. And either the user suffers this, this fundamental property of distributed systems, that everything isn't consistent always, or we as application developers end up putting all kinds of workarounds in, including, horrifically, thread.sleep, until we can guess that some data may have been replicated. Why didn't this work properly? Eventual consistency. Okay, we can do better. Neo4j does better. In Neo4j from 3.1 onwards, we have this notion of a bookmark. And all it is a token. It's an opaque token that represents the user's most recent view of the graph. And we can use it to make sure that we never go back in time. That's what causal consistency is. So let's see how we build this app with causal consistency. So I'm going to create an account. That's going to send some message to my app server. The app server has a Neo4j driver in it, which sends a message to the database. And now, as you can see, records get added into my logs, and ultimately, new nodes appear in my graph. Okay, now I get, you need to log in to continue your purchase. Fine, I log in, send the message over to, in this case, a different Neo4j database that doesn't yet have my user record. This should be slightly worrying. But what I do is I just wait a little while until that's propagated over. Now, and by the way, this is milliseconds, right? This is kind of, from human scale, unnoticeable. Now, actually, the transaction has been applied to my replica. I can service the query and send back to the user. Yeah, so effectively now, these bookmarks allow me, what's happening technically here is that these bookmarks are tied to transaction IDs. Transaction IDs are strictly monotonically increasing integers, which means effectively whenever I present myself to Neo4j and say I would like to run this query, I can now say no at or after this level. So if I've got, in this case, transaction 11, I can say please process this query once you've applied transaction 11 or beyond to your local store. That's really nice, right? Because now the graph always appears to be completely consistent everywhere from the end user's point of view. But the fault tolerance is respected as well, right? So we use Raft to do our, we use Raft and log shipping to transmit user data around the cluster, and there's no corruption here. We always have completely safe, in the absence of non-pathological failures, we are completely safe. In the presence of pathological failures, we become read-only. The transmission of data, replication of data is safe and transactional. The replication model retains our amazing high-performance pointer chasing for reads. We don't do over-the-network traversals. We don't do expensive hash lookups. What our promise is to you, that even as our fault tolerance protocols evolve and our clustering protocols evolve, we will still retain that high performance pointer chasing or that high performance model, because we own the entire database and we can build the database to be respectful of that. We're not handing off the job of doing the hard DBMS work to some other database. So what happens then if you push Neo4j as a native, and this is an Oak native to the UK, push it to its limits? The results are pretty amazing, actually. So if we have a look at a realistic data set from Amazon, we took a commodity dual Xeon processor server, so actually something that's nowadays feeling a little bit dated. We wrote a social recommendation, which is something that you bought connected via something that someone else bought to something that they bought. So it's a social recommendation. It's kind of a friend of friend bought something, or friend bought something. We took that and we ran it on our commodity dual processor server. And what we found was that with single thread, we could do about 3 to 4 million of these business meaningful operations per second. At 10 threads, we could do about 17 to 30 million. At 20 threads, 30 odd to 50 million. And asymptotically, about 30 threads, we topped out at about 60 million of these per second. That's a lot of business meaningful work. I think a recommendation is a pretty mission critical piece of kit for folks selling stuff. So on this native platform, you can absolutely do a boatload of work per second, which means you can put this algorithm, even though it touches your database, you can put it in the clickstream. In terms of scale, when you push Neo4j hard, it can comfortably handle 1 trillion relationships. In fact, I looked in the source code a few days ago at some of the pointer sizes, and it was somewhere in the region of 280 quadrillion items was the asymptotic limit. We can sustain over 100,000 user transactions a second, even when we've got loads of page faults because of having small RAM. You don't have a 512 gigabyte RAM machine for important production cases nowadays. You have a terabyte, or you have 2 terabytes, or if you're particularly feeling deep pocketed, you have 12 or 16 terabytes and some of this kind of more modern, rentable but fancy hardware. So this is amazing, right? This is trillions, as Professor Cox says. That's not an actual celebrity endorsement, particularly because Professor Cox also appeared at a different databases conference, so this is a bit cheeky. Write scale, we imported the Friendster data set. It's about 1.8 billion relationships. It takes about 20 minutes. That's about 1 million writes a second. Millions and billions. This is very, very performant. Still not a celebrity endorsement. In terms of transactional updates, even on my laptop, I can get several thousand ACID transactions a second through Neo4j. That's a lot of headroom, even on some very, very poor, relatively poor hardware. Let me put it in, big bold for you. That's 1 million writes a second on 1 billion records at greater than 50 million traversals a second. That is a lot of horsepower that you get from native technology. So let's compare. I saw on the internet some guys that had built a non-native graph library on top of a different database, a column database, and they said these are their new improved benchmarks. I thought, well, that's interesting, and I generally didn't know how Neo4j would perform compared to this. And they have 10 million node, 100 million relationship graph. So that's the kind of thing that in Neo4j we would trivially spin up and kill for the routine QA that we do per build. It's a fairly modest graph. I took the DBpedia data sets, which is comparable in size, 11 million nodes, 116 million relationships, and they ran their experiments on 288 cores with 1.5 terabytes of RAM in aggregate. That's what these 6 machines add up to. I ran it on 1 core with 8 gigabytes of RAM given to Neo4j. And what happened? Well, for counting nodes in a graph, they're 201 seconds. I did it in less than a millisecond. I don't know exactly what my timing was because I only bothered to time it to millisecond precision and it came up at 0. So that's less than 1 millisecond. Counting relationships, less than 1 millisecond. When I told my engineers about this, they said, hey, Jim, this is not really a fair comparison because they have to actually do a bunch of hard work, networks involved, clever DBMS exercise happens, and we just go to one of our statistics stores and ask, and it's 0.1 for us. I said, yeah, that's exactly right. It isn't apples to apples because our apples are native graph. So even down at the store level, we can optimize for these kind of common use cases. We can do something that takes 3 minutes plus in a non-native case on a beast of a cluster, and we can do it in less than a millisecond on a laptop because we're native. Count outgoing wells at depth 2. So that's friend of friend, 276 seconds on their beast of a cluster, at 1/10 of the time on my laptop. Count outgoing rolls at depth 3, 511 seconds on the beastly cluster, 423 seconds. So actually only 80% of the cost. I ran that one actually on Michael Hunger's workstation. Many of you will know Michael. He had more RAM than me, so he was able to give me twice or 4 times the RAM. Count property values, 212 seconds to 8, 20 odd times faster. Group relationships by type, by friend or bought or likes or whatever, 4 times faster. Count patterns, knows, and likes at depth 2, twice as fast. And importantly, and surprisingly here, given that the non-native setup had these massive, powerful machines, when we ran PageRank, we were 100 times faster, give or take. 2,500 seconds versus 27 seconds on Michael's desktop. It's a good desktop, but it's a desktop machine. So this native advantage just surfaces as incredible performance advantages for graphs on very, very modest hardware. And sure, I would love to be able to tell you, let's build a Neo4j cluster with 40,000 machines. But actually, because we're native for graph workloads, we're quite lightweight. You don't need 6 machines with 256 gigs and 50 vCPUs and loads of RAM. You need a much more modest number of machines when you're running graph workloads on Neo. So just one more thing before we get to Q&A. It's no good having this amazing technology if it's impenetrable by the interfaces. Cypher is amazing. The thing on the left is the same semantically as the thing on the right, and it's effectively finding reporting lines in a system. Cypher eats complexity for breakfast in a way that SQL and other non-graph languages simply don't. So when you're thinking in graphs, it absolutely pays to have a query language that supports your mental model. The affinity between what you're thinking and what you're typing, the whole model all the way down the stack, should be optimized for graphs. You shouldn't have to break out into a world of set unions and joins and all that kind of stuff, when really you're trying to think about a tree in this case. Through OpenCypher, Cypher is now extended its reach. There are demos of it on even on Apache Spark at this point for graph processing. So ultimately, we give you this amazing performance, this really, really humane and lovely query language, and it's native all the way down. So why should you care about native graph tech? Performance, super, super fast, even on commodity hardware, super lightweight. Safety, ACID transactional, don't compromise on the quality and safety of your graph data. And its usability, you've got faster time to value with Cypher, ease of evolution. Neo4j doesn't demand of you that you set your schema up front at the point of least knowledge. You can evolve it over time as your understanding of your problem domain evolves. And you've got a range of amazing ecosystem tooling centered around this graph native tech, and that's growing. And I'll leave you with a tantalizing hint there that if you're interested in learning more about this ecosystem tooling, our Graph Connect conference in New York in October, there are going to be some pretty amazing announcements there. So finally, thank you for listening, everyone. It's been wonderful to be able to speak with you. I'm now going to throw the floor open and ask Angelica if we've got any Q&A.
Hi, thank you so much, Jim. That was a great presentation. And just a reminder to everyone who's with us, we will email a recording of the presentation you just saw and a copy of the slides to you over to the email that you used to register for the webinar today. So we are a little bit over time, but I think we can just take one question if that's okay. So Jim, could you please comment on databases that offer mixed mode storage?
Yeah, so databases that offer mixed mode storage, they generally don't, right? So you've got these things called multi-model databases, and often the ones that I'm aware of, which my confirmation tells me is therefore all of them, they have a model which they choose as their main model. It's typically documents if you look at some of the popular ones. And then on top of that, they try to impose some kind of linkage between those documents that reifies as graph. But unfortunately, if you've already baked in support for documents, you've already made a bunch of fundamental implementation choices. That means that you are probably going to be doing things like index-based lookup versus Neo4j, which has a completely index-free adjacency, so much cheaper. And then in order to support graphs, to support those kind of referential integrity constraints, that it's easy for us to support having graphs all the way down the stack, you have to rely on things up the stack to deal with that. Ultimately, I'm going to say that puts the sanctity of your model at risk, and our experience is you certainly can't perform graph workloads the same amazing performance Neo4j has if you're having to do translations between models. So I think, again, falling back to that Unix philosophy, if you've got a graph workload, get some graph tooling. If If you've got a document workload, get some document tooling, and so on and so on. But don't try and repurpose your document tooling for graphs or vice versa, because you're going to get a poor experience.
Great. And sorry, actually one more. Do we need to get developers to think differently in order to identify best use cases for graph?
Yeah, so look, right, although I'm kind of like this graph evangelist now, having been steeped in it for almost a decade, all of us are quite used to the relational model, and we're quite used to the normal forms of the relational model. You know, we're quite used to modeling in it. The hardest thing in coming to graphs is letting go of what we know. So Mark Needham drew a beautiful chart showing a big curve, a big hump, and you have to get over that hump before you can really love graphs. And the problem I had, and anecdotally talking to other people, even on the Neo team that have done the same, is you know relational in particular so well. And when you come to graphs, you're like, hey, where's my first, second, third normal form? There isn't one. Okay. What are my rules around denormalization? Well, you don't have to. Oh, well, ooh, oh. And so there are a bunch of common practices, almost putting us on rails that we're quite used to with relational. When you come to graph and you find that there are no join tables, it's like, whoa, suddenly you start to love them. You're like, whoa, where are my join tables? I'm quite used to those affordances. And when I tell you you don't need them because in graphs you can join anything to anything multiple times, suddenly you start to worry. But once you're over that hump, when you've got a bit of graph dirt under your fingernails, you start to realize that many of the things that we had to work hard at in the relational world in particular were simply there to help the database do its job. They were accidental complexity. Once you're over this hump and you're in graphs and you realize that what you draw on the whiteboard is what you store in the database, you start to sort of breathe a sigh of relief and realize, actually, now I'm able to tackle the complexity in my domain rather than having to tackle the complexity of my data equipment. Now, there's nothing I can do to make this easier for you. I can recommend literature. I think the O'Reilly Graph Databases book is great, partially because I wrote it, but also there are a plethora of other books out there that will help you get over that hump. On the Neo4j website, there's a bunch of stuff around graph modeling, which I think is particularly helpful for getting you out of relational into graphs. But once you're over that hump, you'll never go back because you'll realize just how complex and unwieldy relational is.
Great. Thank you so much, Jim Weber, for that excellent presentation. And thank you to our audience for joining us on a Friday morning. We appreciate that. So as I mentioned before, we'll send you the recording of the session and the slides just in the next few hours. So keep an eye on your inbox. And thank you again for joining us. Have a great rest of your day.
Thank you, everyone. Bye-bye.